It is the end of 2017, and this has been a great year for Software Engineering Daily. We're taking a break over the holidays, but we're going to be back after New Year's with a lot of new content. And for now, we are replaying a few of the most popular episodes from the 2.5-year back catalog of Software Engineering Daily. And we've removed the ads to make for a smooth listening experience. If you're taking some time over the holidays to listen to some Software Engineering Daily, take a break from your interaction with the family, go for a walk with a nice old episode of Software Engineering Daily, you won't have to skip over any ads or feel obligated to listen to the ads to support Software Engineering Daily. Consider this a vacation for the both of us. We have big plans for 2018. We've got new types of content coming. We've got more in-person events, meetups, but also more of the same. Long-form interviews about technical software topics. That's what I love to do, and I think that's what most people are listening in for. And as we make our way into the new year, I would love to hear from you and know what you're interested in hearing about for 2018, or who you are, or basically anything. Send me an email, jeff@softwareengineeringdaily.com. Join our Slack channel. You can find a link at softwareengineeringdaily.com if you want to talk to more engineers within the community. And you can also sign up for our newsletter, which you can find on softwareengineeringdaily.com at the top of the page. In the newsletter, we will let you know about upcoming live events and other developments within the world of Software Engineering Daily. As always, thanks for listening and happy holidays. D. Sculley is the first author of the paper Machine Learning, the High-Interest Credit Card of Technical Debt. D., welcome to Software Engineering Daily.
Thanks for having me.
Let's start off with a definition. What is machine learning?
So machine learning is, you can think of it as the intersection of statistics, computational power, and engineering. Machine learning is the ability, or the science really, of learning from large amounts of data and to develop systems that exhibit behaviors that we can't really define by sitting down and thinking of all the if-then rules. So we learn those rules from data.
So to quote your paper, machine learning offers a fantastically powerful toolkit for building systems quickly. Why does machine learning allow for complex systems to be built quickly?
So let me give you an example. If you want to develop a spam classifier, so a classifier that will determine if an email is spam or not, one way you could do that is by sitting down and thinking of all the different ways that a spammer might try and get you to read a message. And they might throw some funny characters in a message, or they might say, buy a Viagra, or who knows what. And you could try and list those all, but that would take you a long time. And even if you sat down and thought of 1,000 or 10,000 or 1,000,000 of these rules, it would be rather brittle, and the spammers would be able to come up with some new thing that would defeat your system quite quickly. But if instead you develop a system that allows you to learn from data, then you don't have to spend all the time of thinking of those individual rules. You'll be able to learn those rules from the data very quickly, assuming that you have a large amount of data, and develop the system in quite a bit less time.
Great. And so your paper argues that machine learning has all these great features, but it often leads to technical debt. How do you define technical debt?
So technical debt is not our metaphor. I think Ward Cunningham developed this metaphor a while back to help sort of serve as a way of thinking about the costs of moving quickly versus moving well. When developing software, it's very easy to get into modes of sort of adding on an additional feature or using cut and paste methodologies or any sort of way of writing code very, very quickly that's not particularly maintainable. And as we do that, we accumulate technical debt. And this debt metaphor is interesting because it's something that we can say allows us to sort of take on a cost. And if we pay that cost off the same way we might pay off the cost of a mortgage, everything's okay. We can move forward that way. However, if we're not aware of the debt that we're taking on, or if we take on too much debt, that can really have quite dramatically bad consequences.
Right, and we'll get into the concept of hidden debt further on, but can you talk more about this compounding aspect? Why does technical debt tend to compound just like financial debt?
That's a great question. First of all, this is just an empirical finding. It seems that when we acquire debt, we tend to acquire more and more debt over time in a technical debt sense. And I think that this is in part because once you have a project or a piece of code that has some technical debt, it's probably something like an API that might have been widened too much, or there's 6 pieces of cut and paste code. It can be quite difficult to add something in a clean way that reduces that debt. So instead, the temptation is, I need to move quickly. There's all this cruft around. I'll just add a little bit more. And the more cruft there is, the easier it is, and the more tempting and more difficult it is to avoid the addition of more and more cruft.
And why is it so easy to accumulate massive ongoing debt, this maintenance costs, when you're building machine learning systems?
Well, that's really interesting. It's something that I don't think was widely appreciated, even a year or two ago necessarily by the broader community. Certainly, the people who have been working on machine learning systems have found this to be true. And when we've talked about this work, we've gotten sort of almost Oprah Winfrey moments of, oh my goodness, I'm so happy that you've talked about this. This is something that we've all been experiencing, but nobody has said. So this isn't a novel finding by us in any way. We were just the ones to take the time to write it down. What's interesting about machine learning systems is that they have all of the same problems in terms of technical debt opportunities that traditional software does, because machine learning systems are built off of code. So if we have problems around testing or bad APIs in our machine learning code, that's an area for debt. But then they have a number of additional areas that are sort of unique to machine learning, that are all essentially rooted in the problem that machine learning systems solve problems that we can't formally define. And so we need the data to do that definition for us. We need the data to guide our system behavior. And because of that, data ends up being a vector for increasing technical debt that's really quite tricky to think about.
And your paper suggests that machine learning can lead to this hidden technical debt, as you've mentioned already. What is hidden debt?
So hidden debt I would define as technical debt that we aren't really aware of. So you can imagine if you use a credit card to buy a purchase and you're aware that there's an 18% interest rate, that's one thing. If, however, you're a college student who just got a credit card and didn't necessarily read all the fine print, and you go off and buy a new sofa, that might be a very another thing.
Right. Okay. So, and getting into like the root causes of why a machine learning leads to this debt. One thing you talk about is that complex models erode boundaries, and in machine learning, you're oftentimes making models. What do you mean by these complex models eroding abstraction boundaries?
Yeah. So in traditional software engineering, one of the ways that we can manage our system complexity is by the idea of encapsulation, and basically making one piece of code do one thing. So we do this by data structures and abstractions and good APIs and things like this. But at some root level, a machine learning system is a system that takes many different information sources and mixes them together in a way that we can't define. And this leads to almost a crazy erosion of boundaries, where we can't really say that we can take any particular part of the machine learning system and abstract it out in a carefully defined way. This leads to a situation where changing any one part of the system behavior leads to potentially changes across the entire system.
Could you give an example of this?
Sure. So let's say, all the examples that I'm going to talk about are hypothetical, just for background here, but they're rooted in experience. So let's imagine we've got our spam classifier that we were talking about earlier. And we've found that it does a particularly bad job at classifying spam in Iceland, because the Icelandic spammers, for whatever reason, have a totally different way of approaching the space. And so we might try and correct for that by maybe adding some new features that are specific to Iceland. Or maybe we tweak our regularization parameters or other machine learning settings that change the system behavior. And in doing so, we may discover that the prediction behavior on the Icelandic spam gets improved. But suddenly the spam in Sweden becomes less easy to detect because before maybe some of the credit that was being assigned to Icelandic spam was in this geographically horrific metaphor was being assigned to Sweden, and then by separating these out, we allowed the model to do suddenly different things in ways that we didn't intend.
So from a more high-level perspective, why is it so hard to maintain abstraction boundaries in a machine learning system?
That's a great question. Part of the issue here is that the abstraction boundaries are not really defined. When we have a piece of code, we use that, or a library. It's intended to exhibit a certain behavior. As we mentioned before, in machine learning land, the behavior is defined by the data, the combination of the data in the system, but mostly by the data. And so the natural world produces the data, and the natural world doesn't really have any prior need to have strict abstraction boundaries.
Okay, that makes sense. Yeah, you write that arguably the most important reason for using a machine learning system is precisely that the desired behavior cannot be effectively implemented in software logic without dependency on external data. So are you saying that machine learning is the marriage of hard-coded software logic and constantly changing external data?
If I was to weigh those two things, the external data is in many ways more important than the hard-coded logic. The hard-coded logic that we're talking about here is some sort of optimization algorithm. We can pick your favorite. But the optimization algorithms inside the machine learning systems react very strongly to changes in the data. And so it's the data that drives the changes for sure.
Another definition that you give is that, quote, a machine learning package is a tool for mixing data sources together. Why does this entanglement of data sources make it so hard to isolate different components of the system and to make improvements?
Let's see. So one of the things that we try to do when we're making predictions is to be as accurate as possible. And to do this, we'll often try and take many different factors into account. So in our email example, maybe we'll take into account the email address that the email is sent from, maybe the routers that it went through, maybe the text in the email document. All of these things are different signals that we don't necessarily know in advance how they should be weighed. Is the subject heading more important? Is the subject heading only important if certain words in the document text appear? Is this particular router only important on certain days of the week? We don't know in advance. And so that's why we need machine learning to help us resolve these different kinds of ambiguities.
Right. And one other way that you can mitigate this problem is you can isolate the models and you can serve ensembles. Can you explain this in more detail? Can you give an overview of how ensembling in a machine learning system works?
Yeah, so one of the ways that you can do well in machine learning is by creating different models from slightly different data sets or different signals or maybe with different algorithms. And these models may have uncorrelated errors. If the errors are uncorrelated, then when you combine them together, maybe even just by simple averaging, you will get a better prediction on average in the end. So it can be tempting to say, okay, well, we might try and get some sort of decomposition of our problem by decomposing our prediction problem into different ensemble models. If we have a number of areas that do truly decompose, this might work out. So for example, in our email situation, if we wanted to solve the Icelandic spam problem by taking all of the Iceland data and siphoning off completely to an Iceland-only model and then only mixing at the end where we maybe decide which country model to go to, that might work out. But if instead we've got an ensemble of, say, a random forest and an SVM, which are two different machine learning methods, and mix those together at the end, the fact that those errors are decorrelated was one of the big deals. If we then go and try and improve one of our models, it might be the case that we make one of our component models in the ensemble more accurate. But in doing so, we might make that model's errors more correlated, not less correlated, and actually decrease the overall system accuracy. Exactly the opposite of the intended effect, and exactly the opposite of the effect that we were observed at the component model level.
So do these correlated errors, do they tend to be more common than you would expect?
Certainly, error correlations can happen anytime that you've got quirks in the data, and experience has shown that the data is often quirky.
Okay. So another concern of machine learning systems is what you call a hidden feedback loop. What is a hidden feedback loop?
Yeah, hidden feedback loops will wreck your day. So you can imagine a world where, let's say we're trying to predict spam, and we make a model, we train it off of a bunch of data that we had before, and we release it into the world, and it goes off and it marks a bunch of data, or a bunch of spam correctly, turns it off, well done model. And then on the next day, the spammers realize that their spam isn't getting through, and they try and do something else. They, instead of selling Viagra, they sell some other drug. Now the model needs to react to that if we're going to have any chance of having a healthy ongoing system. So what do? We take in the new data, we feed it to the model, and the model updates itself, and hopefully we send out some updated model that then has a new effect. Now you can imagine that this creates the opportunity for the model to essentially influence the way that it's trained. And this is something that essentially breaks any of the theoretical guarantees that we have for standard supervised learning algorithms. These algorithms do not account for the sort of interaction with the world component. So things can get quite hairy.
So systems that use machine learning often end up with what you call high-det design patterns. What types of anti-patterns should be avoided by machine learning engineers?
So one of the big ones that we've seen is the use of glue code. So by glue code, I mean any sort of code often written in some scripting language like Python or Perl that allows you to get data from one system into another. This glue code design pattern happens quite naturally because not everybody is an expert at writing machine learning code. Oftentimes it's more convenient or more cost effective to maybe take a machine learning package, maybe from an open source area or from the cloud, or maybe it's a company-specific package, and then to try and use that to your own ends. Reuse is generally seen as a good thing. But each package probably has some specific data format, and it has some quirks to it. And so you need to get the data maybe from your repository into the right formats in the right way and send it back to be trained. Then you need to get the data out. We can now have a trained model. We need to put it into serving in some way and allow it to impact our system. So that, again, requires some amount of custom code to be written. None of this is really a surprise, except that because there isn't really a standard set of APIs to be working with, if we then want to change the machine learning system that we're using at the core, we've got a real problem because we essentially have to rip out all the glue code that we've written and replace it from scratch, and that's very high cost.
Right. So you talked about glue code. There's also an anti-pattern that you discussed called dead experimental code paths. And you give a really grim example of this, which is Knight Capital, which probably listeners have heard of. If they haven't, Knight Capital is this company that lost like $465 million due to unexpected behavior. And as you discuss, the unexpected behavior resulted from obsolete experimental code paths. So do you know any more about this example? Like, what were the obsolete experimental code paths that led to such a giant loss of money for Knight Capital?
So one of the ways that we've certainly seen in a variety of different machine learning projects is that because it's quite difficult to, say, rip away all your glue code and start with an entirely new machine learning package, if you have some algorithmic tweak that you want to try, you might implement it as a little conditional code path in your machine learning system. So rather than, if I want to say try a different way of weighing the data, instead of ripping out my package and putting in a new package that knows about weighing data in one way or another, I might just add in a couple lines of code in one place. Okay, now I've got a branch, and maybe I activate it with some flag or some configuration setting. Then somebody else comes along and they've got a different way of tweaking learning rates or regularization parameters, or they decide that they need to do a certain kind of data cleaning. And what you have quite quickly is a large combinatorial set of possible branches that all need to be explored and arguably really need to be tested if they're going to be used. Testing a combinatorial explosion is obviously not something that's going to work well in the long term. So I can certainly speculate that this is the sort of thing that might have led to what we saw with the Knight Capital experimental code paths.
Yeah, and I think like the end result was something crazy. Like they were like trading. They were on opposite. Knight Capital was on opposite ends of one trading position, and they were just like making this trade repeatedly and just losing money on every transaction. And they were basically like the buyer and the seller. So that was the manifestation of the money loss that resulted from the experimental code path.
Certainly, technical debt has real costs.
Right. Okay, so in order to maintain system health, how should programmers manage their experimental code paths?
Well, first of all, it's important to be disciplined, and that's maybe one of the central points of this paper, is that the discipline matters. And here, the discipline is the discipline to go back and look carefully at each of the experimental code paths that we put in and decide if they're still relevant. If they are relevant, then we need to take the time to refactor them into some, well-testable kind of framework. If they're not relevant, then we should delete them. And taking the time to delete code is an activity that everyone should praise at all times, because every piece of code that is deleted is one more piece of code that doesn't need to be tested, and maybe a whole branch of experimental combinatorial code paths that don't need to be worried about.
Okay, that's great. So machine learning systems often have to interact directly with the external world. How does the instability of the external world lead to technical debt within a machine learning system?
So in some sense, the existence of the instabilities is a vector for technical debt in and of itself. You could call this instability debt to some degree. So imagine that we had a hypothetical system for predicting shoe sales. So this model is really good at figuring out when people will buy shoes. It's going along. In October, it's doing a good job of predicting shoe sales. It's going along. November hits, Black Friday hits, and suddenly everybody in the world is buying shoes because they want to give them as holiday gifts. The model sees this and says, oh, wow, shoes are hot. Everybody in the world is going to buy shoes, and it changes its internal predictions. What happens the next Monday? Or what happens, say, through the holiday season on January 1st? The model now needs to react again. How quickly does it react? Well, that's some combination of how often we retrain it, the amount that we allow it to weigh recent data versus previous data, and the various features that we give it. There's going to be a balance, and managing that balance is something that's very difficult to do a priori.
And one of the methods for managing that balance is what you call a decision threshold. What is a decision threshold in a machine learning system?
So oftentimes we want to use a machine learning system to make some kind of decision. In the spam classifier case, we have to decide whether to show this email to the user in their inbox or whether we put it into some spam folder. And we're going to probably need to decide yes or no. And so we'll need to take some score, maybe some probability of spam, and put a threshold on it. Now, that threshold is a brittle thing. It's probably some number. And it might be the case that if maybe the incidence of spam rises dramatically because of some external world factor, that particular threshold might become obsolete, especially if it's manually set.
And how could you update that decision threshold over time?
So the decision threshold is sort of one instance of sort of the manually set knobs. Obviously, in machine learning systems, we would like this sort of knob to be learned from data as often as possible. But in the end, there's always going to be some number of knobs that need to be set by hand. In the threshold case, it might be that we're setting the specific threshold, or it might be a more subtle form of threshold, like saying that, okay, well, we want to be 95 or whatever percent precise, or have X percent recall. And maybe that set of trade-offs might change over time. And it, again, would manifest itself as some sort of knob about false positive versus false negative rates.
Interesting. So another challenge of machine learning systems is this monitoring and testing aspect. Why is it so hard to monitor and test a running system?
So I view, so first, to say what I mean by monitoring and testing, on the testing side, I view testing as things that happen offline, and monitoring as things that happen in the online case. So if we want to focus here on the online case, where things are happening in the real world, we can have a very well-tested system, but it could still be subject to changes due to world behavior. It could be changes in the input signals. There could be changes in some pipeline upstream, all of which could influence the behavior of our system, even though the specific code within our system is very well tested. And so we need to pay very close attention to both the inputs and the outputs of our system at all times to make sure that nothing is happening that's unexpected.
So your paper makes some conclusions about how machine learning can create technical debt, which we've discussed. How can we pay down this technical debt?
So, we can talk about a 12-step plan that, starts with recognizing that there's a problem. And that's certainly one of the areas that I think is most important. It might be the main contribution of this paper, is just helping people realize that there are real opportunities in their systems to clean up technical debt. And then taking the time to prioritize the costs of paying this down. Because when you are paying down technical debt, this is something like taking the time to refactor your systems, or taking the time to figure out how to better monitor your systems and implement that monitoring. It looks like removing signals that you no longer need, or deleting code paths that are no longer required. All of this is work, and work is expensive. And it's time that could be spent doing other things like improving your signals or creating different models. And so prioritizing that work is important. Oftentimes that's sort of a management decision, and being able to make the case that, look, this isn't just a pain, it's an actual ongoing cost that's going to compound, can maybe help management folks make those kinds of decisions in a more rational fashion.
Is there any techniques or strategies for measuring how much a certain piece of technical debt is impairing you, particularly in the realm of machine learning?
So this is obviously it'd be wonderful if technical debt were a metric. Unfortunately, it's a metaphor. But so there's some sort of gut checks that we can do to figure out sort of what is the state of our system. So one gut check is to sort of ask ourselves, how much would it cost and how much effort would we have to take to try a new algorithm or a new approach? Is that something that's relatively simple, or is it going to be, oh my gosh, we have to rip out all this glue code and we have to completely start from scratch? The sort of qualitative answers to that can be quite informative. Simple things like, do we know where all of our data is coming from? Can we track the transitive closure of all of our data sources? And do we know which of these are stable and not stable? That can give very good insights into how much technical debt is in our system. And then figuring out how carefully we can measure the impact of each of the changes that we put forward can be a useful way to assess, any sorts of feedback loops or things of that sort. So it's not a science, and certainly technical debts is not a strict metric, but there are some things that we can do to get qualitative handles on this.
You write that perhaps the most important insight to be gained is that technical debt is an issue that both engineers and researchers need to be aware of. So how can engineers and researchers work together to reduce this technical debt? And what is the dichotomy between a researcher and an engineer? How are their concerns separated when working on machine learning?
So I think in an ideal world, engineers and researchers work very closely together, and in fact are often the same people. I believe very strongly that machine learning projects work best when there's a heterogeneity of expertise in the systems, in the teams. Um, so machine learning has really been an empirical field in many ways, and many of the best successes that have come out of machine learning, especially in recent years, have been the marriage of a useful algorithm with incredible infrastructure that allows it to work at scale. So this can only happen in a sustainable way if those incredible infrastructures are built with really clean APIs and are easy to test and easy to maintain. This is extra work on the part of the algorithmic designer because it can be quite a bit of hassle to figure out how to structure an algorithm in a way that it can be implemented in a testable fashion and with a clean API.
Yeah, I mean, speaking of this, we did a week of shows about data science, and one of the recurring problems in this relationship between data scientists and engineers seemed to be that the data scientists would write a model in one language like R or Python, and then they would hand that model off to the engineer to go implement it in Java. I mean, have you seen this disconnect in languages lead to technical debt?
So certainly one of the patterns that I tend to worry about is if you have a system that's written in multiple languages, this may be an indicator that you have quite a bit of technical debt. But additionally, I tend to be very wary of prototypes in machine learning systems. It's tempting for researchers to say, well, look, I need to work quickly. I want to write a paper next week. I'm going to write a quick prototype in some prototyping language. However, if all we do is prototypes at the research level, then the transition into full-scale systems is horrific. It can be extremely expensive to take a small-scale idea and turn it into a large-scale system. The other thing that's maybe more of an issue is not just the cost, but the fact that the large-scale system is going to have different behaviors than the small-scale prototype does. So the insights that you gain from the small-scale prototype might not even hold at full scale, because changing anything changes everything.
What advice would you give to these types of organizations that have some people working in Python or R and then other people working in Java?
So my basic advice is that folks who are working in machine learning systems should be making sure that their full-scale system is robust and flexible enough to allow for experimentation and algorithmic development.
So are you saying that you think that the people who write the models should be the same people who implement them?
Certainly, I think that's the best way to go. Yeah. And this requires system design to be extremely careful so that there's enough flexibility in the system to be able to do this in a maintainable and sustainable fashion.
Well, D. Sculley, thanks for coming out of Software Engineering Daily.
Great. Thanks so much for having me. It's a real pleasure.